Logan always thought my exams were fair until this one, right, Logan? All right. Yes, you did. You've got a week now to work on phase one of the project. You've got a little bit of a reprieve from the homework for a while, so you won't have a homework assignment due until the 26th of March. You know what? I just realized, is spring break this week? Huh, interesting. Yeah, spring break is this Friday. It's hard to get excited about one day off, isn't it? But apparently, yeah, spring break is this Friday. Okay, so a week from today, you've got the phase one of the project due. Again, I really would encourage you to read in detail the assignment description that I've given you, and start thinking about how much water are they going to use inside of your network. We're going to be talking about steady uniform flow today, continuing with the trapezoidal geometry and Manning's equation from before. I showed you this video during class, and I think that you should go back through it if you are a Casio user. It's important that you figure out how to solve Manning's equation for a trapezoidal channel. Now, in a normal semester, I would absolutely insist that you are able to do it on your calculator. This semester, you can solve Manning's equation for a trapezoidal channel, if you choose, with Excel. That would be an acceptable method, and I'm going to show you how to do that today with Excel. But I still think that it would be a lost opportunity if you don't figure out how to do it on your calculator, because this won't be the last time that you need to solve for an unknown that's inside an equation. So, you know, Manning's equation is easy if you're solving for Q. You know, if you're given the depth and you know the side slope and the channel slope and the bottom width, then finding Q as the output of the equation is simple enough. But when you have to solve for Y, which appears several places in the formula, you can't rearrange that and algebraically solve for Y in a simple way. It's just much better to use a numerical solver. And so please take the time to watch through this video again and pause it as you go through and make the exact same keystrokes that was made in the demo. We'll go through it the other way today, though. We're going to look at the same problem that was introduced at the beginning of, towards the end of class on Friday. Let's look at this with Excel. So we have, just to review, a trapezoidal channel where the bottom width is 15 meters. We've got 2-to-1 side slopes, and we're trying to push through 175 cubic meters per second of flow through that. And it's a relatively shallow slope. This is even less than 1%, 0.45% slope. And then it looks like this is made out of sort of a typical concrete because we have an N value that characterizes the roughness of that surface as 0.013. So let's look at this with Excel. And as we do, I'm going to rearrange Manning's equation. Here is Manning's equation, as I've shown you before. Remember that Manning's equation starts as an expression that solves for the flow velocity, V. But if we multiply Manning's equation by A, then we can get flow rate, Q, on the left side. And on the right side, R is the hydraulic radius. But remember, hydraulic radius is area divided by wetted perimeter. So the first thing that I've done is a little bit different. This blue arrow says I've transformed Manning's equation by taking the area to the 2/3 power that's inside that hydraulic radius expression, and I'm combining it with this area, which is area to the 3/3 power. Okay, so area to the 3/3 plus area to the 2/3 means in the numerator it's area to the 5/3, and then in the denominator of this expression is wetted perimeter to the 2/3. So the first transformation is just like, what do we mean by hydraulic radius? It means area divided by wetted perimeter. So I've combined the like terms in the numerator, the area terms, and then I've rearranged it algebraically again to isolate on one side of the equation all of the constants that are known. We know N and Q and the slope. So all of that's going to be on the right-hand side of the equation. And then any expression that includes the unknown depth Y is on the left side of the equation. So this is still Manning's equation. It's just I've rearranged it. Okay, so let me start up Excel and let's do this together. Let's find out what is the flow depth that's required for this channel. And I'm just going to take a screenshot of this so that I can paste it into Excel and we have all of the data available. That's not so good. Screenshot and paste. All right. So now I can kind of see the problem off to the side as I work. All right. So the first thing I'm going to put is the flow rate. Let me make this just a touch bigger. Okay, so our Q in terms of cubic meters per second. In the problem statement it says it's 175. And our bottom width of the channel in meters is 15. And we know the N value is 0.013. And the slope of the channel is 0.0045. And finally the side slope is 2. T is 2. So it's 2 units of horizontal for every 1 unit of vertical is how we've defined the side slope. All right. Now, the version of the Manning's equation I'm going to substitute all this into is this one. Okay. So I guess the first thing I need to do is get my formula for W. And let me show you back in, it was table 10.1 where we had the geometric parameters. Here's this. Let me copy that and paste it in. Okay. Yeah. Okay. Because I want to have an expression for W. Okay, so W is, you can see 1 plus t squared to the 1/2 power. Okay, so equals 1 plus t squared, close parentheses, and then take that to the power of 0.5. Okay, so W is 2.23. And the reason why I need W is that the wetted perimeter is going to include that W term when I calculate that. All right, now I don't know what the depth is. I have to start with a guess. So, and you may remember that Dr. Pearson in that Casio demo did the same thing, where the calculator will ask you for like a starting guess. And if you start with a bad guess, then your solution may not converge. Like if you start with a negative number, it'll go out and find some root or a solution to the equation that maybe doesn't apply. But in our case, let's just say a depth of 1 meter. 1, okay? And by the way, maybe I should have put minus signs for all of those if I'm going to be consistent. I was defining each of these variables that are going to go into the equation below. Okay, so starting with a guess of y, then what would be the area in terms of square meters? What would be the wetted perimeter in terms of meters? And then what would be the hydraulic radius in terms of meters? Okay, so here we have the formula for each of these things. So starting with the area. Area is B plus T times Y, and then all of that multiplied by Y. Okay, so the area is B plus T times my guess value of Y multiplied by Y. Now I don't have to anchor those references because I'm not going to be dragging this formula anywhere else. I mean, you can if you want. It won't do any harm. But I don't have to because all of the iteration that I do is just going to be by changing values of y. I won't be dragging the formula elsewhere. Okay, so I've just typed in the formula for the area of this trapezoid based on some depth. And so if the water is 1 meter deep, if you had a 1 meter depth, then your cross-sectional area would be 17 meters because you'd have 1 depth by 15, so that would give you 15 square meters as the rectangular component of that. And then you'd have 2 triangles that were 1 by 2. And so if you take those 2 side triangles and add it together, it's like another rectangle, isn't it? It's like a rectangle that is 1 meter tall by 2 meters in width. And so that would be 15 square meters plus another 2 square meters. And so it makes sense, like if we're just doing kind of a mental reasonableness check here, it works out so far. So that's our area if. So I just want to emphasize that this is initially a guess. And then we iterate. Okay, we'll do that in just a bit. Now let's write the wetted perimeter in terms of this unknown guess depth. And so here's the formula for wetted perimeter. Equals B plus 2 times the depth times W. Okay. Okay, so that is our wetted perimeter if it's 1 meter in depth. And so remember, wetted perimeter is where is the water in contact with this concrete material. So we'll have 15 meters of perimeter on the bottom, and then the other 4.47 comes from the side. Okay. Now hydraulic radius by definition is area divided by wetted perimeter. I can't click there, but I can type it in. B13. Oh, I don't need the parentheses. Okay. Area divided by wetted perimeter. So now we've got the hydraulic radius. Okay, so this is all based on the guess. This is just the geometry. Now what we're going to do is substitute it into the equation. Let me just copy it and paste it so we've got it in the right spot. This equation is the one that I want. So what is the left-hand side of that equation, and what is the right-hand side of that equation? Okay, so the left-hand side of that equation is area to the power of 5/3. And then I'm going to divide that by the wetted perimeter to the power of 2/3. Okay, so if this is our depth, then that's the left-hand side of the equation. The right-hand side of the equation is not depth dependent. It's a constant because it is the n value multiplied by the flow rate divided by slope to the power of 0.5. Okay, so that constant is 33.91. Now let me ask you this. Right now, does the left-hand side equal the right-hand side? This equation says that they should be equal. Well, so far they don't. We have a difference right now. We could calculate the difference between the two. And right now we have a non-negative difference, a non-zero difference. We want the difference to be 0. So we should do a goal seek, right? We should do a goal seek where our goal is for the difference to be 0. Manning's equation says that the area to the 5/3 divided by wetted perimeter to the 2/3 will equal all these constants on the right-hand side. Okay, so here's the last part. We're almost done. We're definitely in the home stretch now. We go to the ribbon across the top, and we go to the Data tab, What If Analysis, Goal Seek, and our goal is to set the difference equal to 0 by changing the depth. And so we started with a guess of 1, and that wasn't right. I mean, we could just do this manually. What about 1.1? That's getting closer because the difference just got smaller. What about 1.2? We're headed in the right direction. 1.8? Oh, that's too far. 1.7? Headed in the right direction again. So you could just manually keep crunching the numbers like that. Or we could data, what if analysis, goal seek, and set the difference to a value of 0 by changing the depth. Okay, so as soon as I click OK, in the blink of an eye, it's going to play around with a bunch of different possibilities, and it finds, oh, did I not tell it to keep the solution? I got to do it again. Goal seek, set the difference to a value of 0 by changing the depth. OK. OK. 1.572. So that is the depth. So our conclusion then, the flow depth will be 1.572 meters for the geometry and flow rate described. Okay, so are there questions about that? Solve it with Casio, and I think you'll get the same thing. All right, so what we did was we took Manning's equation, and for SI units, there's no coefficient prefix in front of it. Remember, for British gravitational units, if you're working in feet and cubic feet per second, then you'd need 1.49. And we're just simply rearranging so that we put any term that has the depth on one side of the equation and putting all of the constants on the other side of the equation. And then we solve it until the left-hand side equals the right-hand side. All right, so we've just done that one. Let me turn you loose on this one. This is actually, maybe I should have started with this. This is even easier because we're just finding that flow rate Q. Rather than solving for an unknown depth, this is telling us we already know the depth is 1.2 meters. And so what's the flow rate here? If we know the depth is 1.2 and it's got a bottom width of 3.5 meters and then our slope S is 0.1%. So that means when you put it into Manning's equation, what this needs to be is as a decimal. So 0.1%, you should write that as 0.001. Okay. And let's see, what else do we know? We know the side slope here. It's telling us it's 2.5 units of horizontal side slope to 1 unit of vertical. So that's defining the T. That tells us T is 2.5. All right, so I'm going to pause for a second. I am going to put you in those breakout rooms, and I'd like you to collaborate together, see if you've got the right idea here on calculating the flow rate. And do I put Manning's equation? There it is, Manning's equation. I've written this one where it's area to the 5/3 divided by wetted perimeter to the 2/3. And you can use this same set of geometry. I wonder if I still have it in my clipboard. No. Let me pull it from here. This. Here's our geometric parameters. It's a bit large, isn't it? Well, it seems like nowhere I put that's going to be out of the way, unless I move all of this to the side. All right, well, I think you've got the idea here. Okay, so I'm going to stop talking. I'm going to pause the recording and give you some time here to calculate what is the flow rate Q that can be achieved through this channel section.
You do pick up the phones in their grass house again. What's their break?
All right, everybody, welcome back. Let's take a look at the solution together, just to make sure that we are on the same page here. So what we are doing is trying to calculate the flow rate Q. We know the depth is 1.2. We know the roughness of the channel, the side slope is defined, the bottom width, and then the slope of the channel itself. So there's two ways to calculate the area. One, you can just substitute it into this formula. That's one perfectly fine way to calculate the cross-sectional area. Or you can look at it and see that we've got a pair of triangles on the side and a rectangle in the middle. So my solution takes that approach. If I just show it to you now here, what I've done to find the flow rate is okay, so if we've got 1.2 meters of depth, and you can see the side slopes is 1 unit of vertical for every 2.5 units of horizontal, then I've multiplied 1.2 by 2.5, and then that gives me that there's the 3 meters on the side here. So essentially I've got the bottom width of 3.5 by 1.2 meters in height. So that's one of the area components here, and then the two side triangles together. So this area of 7.8, that's the same that you'll get if you use this other approach of B plus TY times Y. You should get that the area is 7.8 meters. Okay, so that's the cross-sectional area. The wetted perimeter, you can see 9.96 meters. And now substituted into Manning's equation, we've got the slope needs to be expressed as a decimal. So it was defined as a percentage. 0.1% is how I told you. So you need to divide that by 100, and you get 0.001 is the slope. And so in the end, you should get that the flow rate is approximately 15 cubic meters per second. Any questions about that? All right. Let's take a look at one more example. So we've got, is this the same channel? Yeah, okay, so it's the same channel, 3.5 meters across the bottom. This time though, and same slope, same roughness, 0.014. This time though, we want to put more water through. In the previous example, we calculated that the depth of 1.2 meters is associated with a flow of 15 cubic meters per second. So now what if instead of 15, we put 29 cubic meters per second? Then what would be the flow depth for that? Okay, now you can put it into your calculator, or maybe this would be a good chance to try out the Excel approach. And so I previously had solved this example. Let me just create a new page in this workbook. So I'm going to copy it, and that way I can just kind of use all of the same formulas from before. So this time, I'll delete this. I've got this new problem. I'll paste so that we have it just available to view as a reference. It's the same channel as the previous example, but approximately double the flow. Okay. All right, so now that's small enough that it can be displayed, I think. So our flow rate is 29 cubic meters per second. The bottom width is 3.5 meters. Our N value 0.014. The channel slope 0.1%. So that is 0.1 divided by 100. 0.1 divided by 100. So 0.001. And then the side slopes is 2.5 to 1. So that calculates the W. I'm going to start with some guess of the depth, and if the depth is 1, then I have a certain area, a certain wetted perimeter, and hydraulic radius. So my objective is I want to find out what is the new depth that will make the right-hand side, which is just referring to these fixed constants of flow rate, slope, and N value. How do I make the right-hand side equal to the left-hand side? So right now, the left-hand side is too small. But if I make it 1.5, we're getting closer. 1.6, closer still. So now I do data, what if analysis, goal seek, and I want this difference to be equal to 0 by changing the depth, and let it rip. And it tells me the depth should be 1.66 meters. So I'll now put the conclusion here. The flow depth will be 1.66 meters for a flow rate of 29 cubic meters per second through this channel. Okay, once you get the spreadsheet set up, it can be pretty easy to change. I mean, all we did was copy and paste from the previous example. All the formulas structurally stays the same. It's just some of the geometric parameters may be adjusted. And the same thing is true, by the way, of your solver. Once you type that equation into your calculator, it'll remember it, so that then all you have to do is change the parameters like N and slope and T and so on. So type it in once and then it gets much easier from there. We're out of time. Just in conclusion, remember that it is the design project that is your next submission a week from today. So you should be thinking about how do you turn area and different types of uses into flow rates. I got a good question over the weekend. Somebody asked me, does mg stand for million gallons? And the answer was yes, it does. Mg means million gallons. All right, that's it, everybody. Hope you have a great day. I'll see you on Wednesday.